discussing the inverting amplifier, and two things which we did. One was that the practically used expression for voltage gain with feedback amplifier, this was minus Rf by R1, that is the ratio of these two resistances Rf and R1 that gives the voltage gain. We can choose these resistances in the kilo ohm range to get a particular ratio, and that will be the gain. This was the point which we discussed. Another important point was that V2 was at 0 potential, that means it was at ground potential, and this is called virtual ground. Ground because it is at ground potential, and virtual ground because actual ground can absorb almost any amount of current, but this is a small signal device. So, hardly a fraction of a ampere will be the current which this will be able to handle. So, these 2 points we discussed. Another feature, as it was pointed out, that inverting, non-inverting amplifiers, these are both very widely used amplifiers. So, let us look for other important features of this amplifier. Next parameter is the input impedance. Input impedance of inverting amplifier. For this, we first draw a simple equivalent circuit for an op amp. Equivalent circuit for op amp. Simple, it is this. This is the voltage source, where this is VID, and this resistance is RO, the output resistance, and this is the inverting input and this is the non-inverting input, and here we give the signal Vi2, Vi1, and we take V out here. So, this is the equivalent circuit, and amplifier, we remember that the basic amplifier is this. This is Rf, this is R1, and here is the input for the inverting amplifier. Now, this resistance Ri is quite high here. This resistance, we have been saying that input impedance, first stage of a op amp is a differential amplifier, and differential amplifier has a very high input impedance. So, this is Ri, and it is more than 1 megohms in general. So, we can apply Miller's theorem, which we have used earlier, Miller's theorem. Miller's theorem is applicable to find out the equivalent resistance of this RF at input and output, because this is in Miller's configuration. What is Miller's configuration? One end of the resistor is connected at the input and the other end is connected at output. So, this is in Miller's configuration and we can apply Miller's theorem. So, in that case the impedance which we will be getting is this. This is R1 and this resistance, this is the Miller's equivalent at the input, and this is equal to RF by 1 plus A, where A is the open loop gain, and this is that Ri, the input impedance here, this Ri, and this is in Miller's form. So, we transform it to its equivalent at the input, and this is R1, and of course, here this is Vi. So, at the input the net resistance of the feedback amplifier, this one, the input impedance of the feedback amplifier becomes Zi with feedback. So, feedback amplifier, this is R1 plus this combination in parallel. So, R1 plus RF 1 plus A in parallel with Ri. Now, here A is very large, so this RF will be very close to 0. RF by 1 plus A is close to 0 because A is very large, of the order of 10 to power 5. So, this is almost 0, and any smaller resistance in parallel with a high resistance, the resultant is the smaller one. So, RF 1 plus A in parallel with Ri is almost 0. Therefore, input resistance is only Ri. Input resistance or input impedance, input impedance of amplifier is R1. This is whatever value we choose in the inverting amplifier, the value of R1, that will be the value for input impedance. How simple it is. If you want to have a inverting amplifier with input impedance of say 5 kilo ohms and gain 20, then take this R1 as 5K, and because gain is 20, so 20 times of this, that means 100K, 100 kilo ohms RF and 5K R1 will give input impedance of 5K and gain of 100. Very simple design, and that is one reason of the popularity of op-amp. And from a simpler consideration also the value comes out to be R1. The simpler consideration is that this point is at ground potential, V2 is virtual ground. So, what is the impedance which you expect between these 2 points, the virtual ground and this point R1. So, R1 and from a more rigorous simple analysis, though we have found that input impedance is R1. Now, the output impedance can also be derived from similar considerations, but we are using another concept. Since it is a voltage shunt feedback, which we are using with the inverting amplifier, then you will recall from what has been said earlier when we were discussing feedback in amplifiers, that voltage shunt feedback brings the output voltage down by a factor of 1 plus AB. That is, the output impedance as shown in this equivalent resistance is RO. This RO, because of that feedback, it will be reduced, and this is RO with feedback. This is ZO with feedback is RO 1 plus AB, 1 plus AB, and so this is drastically reduced. Here RO is the output resistance or impedance, same thing at smaller frequencies. So, output resistance without feedback, and A is the open loop gain, and B is equal to R1 by R1 plus RF. So, this way this is drastically reduced, which is again which goes in favor of a voltage amplifier. Inverting amplifier is a voltage amplifier which has a high input impedance. We can choose the value of R1, and gain is high, we can choose the ratio RF by R1, and the output impedance is low as given by this equation. So, this is about the output impedance. Now, so we have done non-inverting amplifier, we have done inverting amplifier, and we have evaluated the basic parameters of the amplifier, and the next is the differential amplifier. We have studied differential amplifier using two transistors Q1 and Q2 and connecting in a particular way, and when we collect the outputs, we take the outputs from the two collectors, then a differential amplifier can be constructed. That is a basic design, and that was investigated for various basic understanding. Actually, instead of using the transistors, discrete transistor units, and then providing a constant current and all that, actually the differential amplifiers are realized by using a operational amplifier and using it in a differential mode. So, this is the basic circuit. gain, open loop gain is A, this is inverting and this is non-inverting input. The batteries, and now here we connect R3, R2, and this input is the voltage is V1, and here we apply the signal source VB. Similarly, here R1, this is V2, and this is RF, and here is the other input signal VA, VB, and this is 1 and 2. So, this is the differential amplifier. Amplifier circuit, and V out, as we have studied in the differential mode, gain into VA minus VB. This is the whatever is the signals which will be available here. V, actually I should have written V1 minus V2 for this, but anyway the difference here that will be amplified. Whatever is the voltage at V1 and V2, the difference will be amplified. Now, to study these two signals, again we take help of the superposition theorem. In such cases, it always pays to apply the superposition theorem, and we will take one input signal active at a time, the other will be grounded. We will see what will be the output of that, and then the other will be activated and the first one will be grounded. Again we will take the output, and net output will be the, by this is superposition theorem, that algebraic sum of the two will be the net output of the differential amplifier. So, remembering this design, this of course we will be needing in our discussion further, that the relationship between input and output voltages can be obtained. Let us take case 1, and case 1 is let VB be grounded. This is grounded, and we are investigating the output because of VA. VA, as you will see, if this is grounded, this is a inverting amplifier. So, we are then having inverting amplifier. So, the output VO because of A will be minus RF by R1 into VA. This is the gain. Gain is VOA by VA, which is equal to the ratio of the two resistances, these resistances, RF by R1, and this is what for a inverting amplifier, this is the gain. So this is because of the first signal source VA active and VB is grounded. We take case 2. Case 2 is let VA be grounded and VB is connected to non-inverting input with resistances R2 and R3. This is implied. So then we are dealing with a non-inverting amplifier. Non-inverting amplifier, and here what is this voltage V1? This will be, this signal source will send a current and that current will be VB by R2 plus R3, and when this current passes through this resistor R3, whatever is the voltage developed here, that will be V1. So V1 obviously is R3 R2 plus R3 into VB, voltage divider. This network is acting as a voltage divider for this voltage. So what is the voltage which will be available at R3 is this, and output due to VB, because of this input signal, the output then will be VOB. This is equal to 1 plus RF by R1. This is the gain which we have arrived at earlier for a non-inverting amplifier. This is the gain, and into the input signal. This VOB by B is the gain of the non-inverting amplifier, which is equal to this, and hence VOB is equal to this. Now we substitute for V1. This V1, and what will it appear at output? This is this, and now we substitute for V1 as we have got here. This is the value of V1 which we substitute, and then VOB is equal to R1 plus RF by R1 into R3 R2 plus R3 into VB. This is the output, and now let resistance R1 is equal to R2. R1 R2 we take identical, and R3 and RF we take identical. So let R1 is equal to R2 and RF equal to R3. Then when we substitute this will cancel, and we are left with OB equal to RF R1 VB. This is the contribution under this condition from the second input source VB. Now we apply the differential or the effective superposition theorem, and then it will be AD, differential gain, which is equal to V0 VA minus VB, and this is VOA plus VOB VA minus VB. This is the general expression for the differential amplifier, and when we substitute these values of the two by superposition theorem, then it comes out to be this, and which obviously is using 1 and 2, it comes out to be RF by R1. That means the gain AD is equal to minus RF by R1. This is under the condition when in this design we have taken R1 equal to R2 and RF equal to R3, which is a symmetrical design which is normally used, and then this gain is this much, and the output will be with this gain and two inputs VA minus VB. This is the difference of the two signals will be amplified, and whatever is common will be filtered out. Another important point is that because the input impedance is different for inverting and non-inverting amplifier, so let us briefly talk about the input impedances of differential amplifier. The inverting part of it, that is RIA, input impedance because of the inverting amplifier, this we know that this is equal to R1. And for non-inverting amplifier, what is the impedance which will be seen here between this and ground? These two in series. So this is 1 and 2 is RIB because of this B, what the B source will see as the impedance, that will be R2 plus R3, and because we have taken it R1 equal to R2, so this is R1 plus RF. The inverting amplifier will see R1 as the impedance, while the non-inverting will see the impedance R2 plus R3, which is equal to R1 plus RF. So this is a important conclusion, that besides the magnitude, the fact is that the impedances seen by two input sources, they will be different for a differential amplifier. Now, so the major three amplifiers which can be easily accomplished with the help of a operational amplifier we have completed, that is a non-inverting amplifier, a inverting amplifier, and a differential amplifier. Now there are some other forms of the amplifiers which are small modifications over this inverting and non-inverting ones, which are also widely used. So let us take one or two cases. The case of a voltage follower, for example. Voltage follower, this is one, and another one which we can study is current to voltage converter. Current to voltage converter. These are both these amplifiers, voltage follower and current to voltage converter, both these amplifiers have a good number of applications and they are used. So, let us see how the inverting and non-inverting amplifiers with little modification can give these functions which find wide acceptability in systems. Let us first take voltage follower. Voltage follower is synonym to what we have done as emitter follower. In discrete circuits with a BJT, we had emitter follower. Now, with op-amp the circuit is voltage follower, and this is, you remember, this is the modification of a non-inverting modified non-inverting amplifier. So, the basic amplifier was this. This is R1, RF, VI, VO, and this is the batteries, the DC sources, and the open loop gain is A. This is a non-inverting amplifier. And this is modified to this form, and how this modification comes, I will just talk. VI, and here this is voltage follower. And how it has been obtained? Here we have made RF equal to 0 in the basic non-inverting amplifier. This RF has been made 0, so it is just a connector here, and R1 is taken as infinitely large, very high value. So, not there. A gap is infinite resistance. So, R1 has been taken infinite and RF has been taken 0. The circuit is reduced to this, and the gain of the non-inverting amplifier, gain of the non-inverting amplifier is 1 plus RF by R1. When RF is 0, then this is reduced to 1. When gain is 1, and then V out is gain into V in, and since this gain is 1, V out is equal to V I. This is what in emitter follower, why, from where the name comes. In emitter follower, the output voltage follows the emitter. Here we are seeing that this output which will appear here, this will be of exactly equal magnitude as input, and the phase will, they will be in phase, that means phase is also same. So, that is why the name voltage follower. Now, you may question that if the same voltage appears and same phase appears, what is the function of voltage follower. The application of voltage follower is the same as for emitter follower, that is as a buffer amplifier. The input impedance is very high, output impedance is very low. So, this can be used to for matching purposes, matching impedances. So, the application is as a buffer amplifier. But it is preferred over emitter follower for two reasons, that the input impedance is much higher in this case, in the case of voltage follower as compared to emitter follower, and here output is exactly equal to input. They are more equal than in the previous case. So, these are the two points. Because of that, a voltage follower, which is a modified non-inverting amplifier, that can be realized, and it is used as a buffer amplifier. Another example let us take, and that is of current to voltage converter. This is a modification of the inverting amplifier, modified inverting amplifier, which can work as a current to voltage converter. There are many situations where such kind of application will be required. For example, in photosensitive devices, photodiodes, the currents are available which will be varying with intensity or whatever it is. So, those currents have to be converted into voltage format for further processing, and so current to voltage converter will be a requirement. Other situations may be in digital to analog converters. There are several sensors which may give a different which will give you the current, and we have to get the corresponding voltage. Now, as I said, it is a modified inverting amplifier. For a inverting amplifier, the gain with feedback which is the ratio of output to input, this is equal to minus Rf by R1. This we have been saying all through, that for a inverting amplifier, gain is the ratio of the two resistances, the feedback resistance and the input resistance, and from here V out is simply minus Rf R1 into V1, or this is equal to minus same V1 R1 Vi R1 into Rf. Now, V2 is 0 here. This was the total amplifier, and now what we are saying, this is the virtual ground V2. V2 was 0 because it is virtual ground. This is V2 is virtual ground. In that case, what will be this current? V I minus V2 is divided by R1 is I1, but because this is 0, so because V2 is 0 as it is virtual ground, the Vi R1 this is equal to I1, and this we can substitute. So this is the current. So what we are getting? We are getting V out equal to minus I into RF, that is output voltage is proportional to the current. This is what is expected out of current to voltage converter, and what we have done, this is RF, this is current I1, and this is same as I here, because this current IB is very close to 0, and we have replaced the voltage source Vi and resistance R1 by its current equivalent, and we get this circuit. And here obviously the output varies according to the input, and hence this is the current to voltage converter. And here, since the output, as we have seen, output resistance of the inverting amplifier is very low, so this current, this voltage developed because of this current variations, this will be independent of the load resistance, because again the same thing, low and high impedances in parallel, the lower one dominates. So because the input impedance is very low, this value of RL does not affect that, and it works in a perfect manner. And so applications, I said photo detector, that photo currents are converted into voltages, and so on. So this is another application. Now moving further towards the application, now we go for amplifiers, that means operation amplifiers for mathematical operations. Applications for mathematical operations. We will take a good number of mathematical operations and the circuits for them, that how we can realize those operations, how those operations can be obtained electronically. Let us start with the simplest case, the sign changer. Sign changer, that means electronics understand the quantities in the form of voltage. So if we can change the sign of voltage, then that is the sign changer, and this can be easily obtained by inverting amplifier using inverting amplifier. This is the inverting amplifier. This is the inverting amplifier. In this, the gain, you remember, the gain is minus Rf by R1, and which is equal to V0 output by input voltage. Now, if we choose here the two resistances as of same magnitude, so R1 is equal to Rf, then this term will be unity, and gain in this case will be 1, and V0 will be minus Vi. And so, and these two will be of identical magnitude because gain is 1. So, the sign has been changed. So, if we want to change the sign, let us use a inverting amplifier with unit gain, then it can act as a sign changer. Now, more important application, more applications of op-amps. So, we go for summing, scaling and averaging amplifiers. Summing, scaling and averaging amplifiers. Summing amplifier. Summing amplifier is the one where there are more than one inputs, and the output will be the sum of all the inputs. If that we can achieve, that will be a summing amplifier. And similarly, scaling and averaging amplifiers we will take one by one. So, let us first take now these amplifiers can be realized either in inverting mode and using inverting amplifier, or by using non-inverting amplifier. To save time, we will go for the case of inverting amplifier. So, let us take first a summing amplifier using a inverting amplifier. What is the basic circuit? There will be more than one inputs, 2, 3, 4, 5, 6, any number. So, for simplicity we take 3 inputs. This is V1, V2, V3 and RF, and this is R1, R2, R3, and this is the inverting input and this is non-inverting input. So far we have been connecting it to ground, but now we introduced another concept. instead of directly connecting to ground, it has been shown that the if we connect a resistance here R x, which is roughly equal to the parallel combination of all these resistances R 1, R 2, R 3, it works better. Here the zero errors, for example, when there is no input signal, the output should be 0. Such conditions, they are slightly better achieved, and hence it is a common practice to use here a resistance of appropriate value, which is given by the parallel combination of these resistances, and that can be connected. So, this is the basic summing amplifier. And as I said, we have taken for simplicity 3 inputs: voltages V1, V2, V3, output V0, and this is a inverting amplifier. Now, first I take a general expression, and then we will one by one we will go for summing amplifier, scaling amplifier, small modifications in the 3, but major thing is the same. So, in this voltage VB, remember VB is 0, a virtual ground. Virtual ground. Now, we will take this and we can write that the currents here, this is I1, this is I2, this is I3. Now, because this voltage is 0, what will be this current I1? I1 will be V1 minus V0 by R1. Similarly, these currents, but this is 0. So, the current is actually V1 R1, this is equal to I1, V2 R2 is I2. So, all these currents, and the sum up of the currents will be IF. We will continue that this simple circuit will give always the output that will be the sum of input voltages, and if these voltages represent numbers 2, 3, 5 whatever, then the output will be the sum of these numbers. So, we will continue this analysis, that from the main analysis we can arrive at scaling, averaging, summing amplifiers, and that all operations, mathematical operations. Then we will go for differentiator and integrator circuits, and so on. We will continue.